Welcome to this lesson about fundamentals of solid mechanics. In this lesson we will deal with the concept of equilibrium of a deformable body, stresses, strains and Hooke's law, shear and moment diagrams and bending stresses in beams, torsion and torsional stresses in beams, shear stress in beams and Jurafsky's formula, deflection of beams, the elastic curve and the Castigliano theorem. So let's begin with the equilibrium of a deformable body, and in particular with loads and reactions. So loads acting on a body can be external or support reaction. For external load, we have surface forces that are distributed over an area. If the area is small, then the force can be idealized as acting on a point. If the area is narrow, it can be idealized as a force distributed over a line. We have also body forces that are forces exerted on a body, for example, the gravitational field, and those are concentrated in the body's center of mass. We also have the support reaction that are surface forces that are applied in the contact between two bodies. For example, when we have hinge, for example, that prevent motion, and there will be support reaction applied. We can enter now into Newton-Euler equilibrium equation. From the dynamics of rigid bodies, we have the Newton-Euler equation are that the mass times the second derivative of the position vector is equal to the total force, which is equal to the sum of all the forces, and the time derivative of the angular momentum plus the velocity cross product, the linear momentum, is equal to the sum of all the moments. Since we are in static condition, there is no variation of linear and angular momentum and no velocity, so the sum of all the forces must be equal to 0, and the sum of all the moments must be equal to 0. Those are vectorial equations, so if we can write down those in terms of scalar equation, and we have that the sum of all the forces acting along x must be equal to 0, and the sum of all forces acting along y must be equal to 0. They also can be said for z, and also for the moments, the sum of all the moments acting along x must be equal to 0, the sum of all moments acting along y must be equal to 0, and the sum of all moments acting along z must be equal to 0. Let's now enter into internal loads. So if we imagine to cut a body with an ideal plane, we will have two bodies at the end, and those two bodies must remain in equilibrium. So in the cross-section, there will be an unknown distribution of forces, and this distribution is actually equivalent to resultant forces, Fr, and a resultant moment, MRO, all applied in the centroid of the cross-section. In general, we can decompose the resultant force Fr in the force V and the force N. The force N is actually a force orthogonal to the cross-section, normal to the cross-section, and the force V is a force tangent to the cross-section. The same can be done for MR0 that are decomposed in MF and T. MF is a moment tangent to the cross-section, and T, the torque, it is a moment acting orthogonal to the cross-section. We can furthermore divide the force V and the moment M in the component along x and y axis. So V will be equal to Vx plus Vy, and M will be equal to Mx plus My. Let's see an example. We have a L-shaped beam with a fixed end, a constant cross-section. We have a force applied in the top face at the center, in the centroid, so a force F, that can be decomposed in the component Fx, Fy, and Fz. So in general, it can be represented as a line here because it's actually a simple beam. And we are interested in finding the internal reaction at the section A and the section B, which are at half the height and half the length of this L-shaped beam. So if we cut our beam at position A, we will have a smaller beam with the previous forces Fx, Fy, Fz, and the internal reaction forces, so N, Vz, Vy, the moment My, and the moment Mz. And we can compute all these reacting forces. So it's easy to compute and find out that N is equal to Fx, Vy is equal to Fy, and Vz is equal to Fz. And the moments are My is equal to minus Fz h half, and Mz is equal to Fy times h half. And Mx is equal to 0 because there is no torque in this case. We can also do this at the M position and decompose the system in this way or in this way if we want to transpose the forces from this position to the elbow of the L-shaped beam, introducing some additional moments because we transport the forces down. At the end, we can find that trivially the normal force is equal to Fz, the shear force along x is equal to Fx, the shear force along y is equal to Fy, and in this case we have that Mx is equal to Fy times L half, My is equal to Fx times L half minus Fz h, and in this case we will have some torque, so Mz is equal to torque, and it is equal to Fy times h. Let's now enter into stresses, strains, and Hooke's law. So let's talk about normal and shear stresses. So we can ideally subdivide a cross-section in small areas, delta A, and if we assume that the material is continuous and cohesive, we can state that there is a force, delta F, acting on this small delta A, and this force can be furthermore decomposed in delta Fx, delta Fy, and delta Fz. This can be done in all directions, and we can obtain a generic cube. So for a generic cube, we can define the normal stress is sigma as the intensity of the force perpendicular to this cube. So, for example, the first perpendicular stress is sigma z, and it is equal to the limit of delta A going to 0 of delta Fz over delta A. The same can be said for sigma y and sigma z. We can also state that normal stresses are called compressive if the cube is pushed, and they are called tensile stresses if the cube is pulled. We can also introduce the concept of shear stresses, tau, and those are the intensity of the force parallel to delta A. So we have tau zx and tau zy, for example, and those are the first, the limit of delta A going to 0 of delta Fx over delta A, and the second, the limit of delta A going to 0 of delta Fy over delta A. These shear stresses has two letters at pedix, and the first letter indicates the direction normal to the face of our cube, and the second direction is actually the direction on which the force is acting. It's important to note that the normal stress and shear stress are defined as force divided by an area, so Newton over square meter, and it is actually Pascal, so they have the same unit measure of a pressure. Let's see an example, a simple example, a bar axially loaded, and we assume that the material is homogeneous and is isotropic, we have a constant cross-section, and the load is applied in the centroid of our cross-section. So Fx is equal to the sum over the area of delta Fx. So if we go into the differential part, we have that the P, the load, is equal to the integral over the area of the F, and it is equal to the integral over the area of sigma dA. So at the end, we have that the load P is equal to sigma times the area. If we isolate an infinitesimal cube, we have that sigma z and sigma z prime, and in this case sigma is equal to sigma prime because we have an equilibrium for the translation. Now we can write down the Euler equation around x and y axis and find out the integral over the area of y df is equal to the integral over the area of y sigma dA, and since sigma is constant, we can bring it out of the integral, and having that sigma times the integral over the area of y dA is equal to 0. And the same can be done for the second integral, and this is true actually because we apply the force in the centroid of the cross-section. We also have an example for shear stresses. So shear stresses are produced by shear force V, and we can introduce the concept of average shear stress as tau average equal to V over A. And if we isolate an infinitesimal cube, we have tau zy and tau yz and tau yz prime and tau zy prime. And because of the equilibrium of the translation, we have that tau zy is equal to tau zy prime and tau yz is equal to tau yz prime. We can also write down the Euler equation around a corner of the cube, and we have that tau zy times delta x delta y times delta z minus tau yz times delta x delta z delta y is equal to 0. Therefore, we have that tau zy is equal to tau yz, and it is equal to tau. Now let's talk about strains. So we can define the normal strain as the relative elongation of a curve along a surface. So the average strain, epsilon average, is equal to L prime minus L over L. So it's delta L over L. And for the punctual definition of the strain, we have that epsilon is the limit with L going to 0 of delta L over L. The strain will be positive if the segment is enlarged, and it will be negative if it is compressed. So here we have a figure describing our body before deformation and after deformation. So here we have the length L, and here we will have the length L prime. We can also define a shear strain as the difference between the angle before and after the deformation. So before we will have, for example, a 90 degrees angle, and after we will have an angle which is actually theta prime. So if we use this definition, we will have that gamma, which is our shear strain, is equal to pi half minus the limit of theta prime with AB going to 0 and AC going to 0. In a generic viewpoint, we can write down normal strain and shear strain for all Cartesian axes, and for a cube of small dimension, delta x and delta y and delta z, a dilatation will produce again a parallelepiped, and we have that the normal strain in this case will be epsilon x, epsilon y, epsilon z, and shear strain gamma xy, gamma yz, and gamma zx. Now let's talk about the stress-strain diagram. So the stress-strain diagram is used to obtain a relationship between the stress applied and the resulting strain. This graph will be obtained through the tension or compression of a specimen. So it will be a cylinder of base area A0 and length L0, made like in figure. And we can define the nominal stress or engineering stress as sigma equal to P over A0. So is the load applied over the area, the nominal area. And we can also define the nominal strain or engineering strain as epsilon equal to delta over L0, where delta is the specimen elongation and L0 is its natural length. Here we have a stress-strain diagram, a qualitative representation of a stress-strain diagram. We can see that there are two regions, the elastic region and the plastic region. In the elastic region, it is the first region, the material is behaving proportionally. So until the sigma PL, that stands for sigma proportional load, then the material tends to yield. So there is an increment of epsilon without an increment of sigma. And after we will start to strain hardening until we start the necking phase, where the cross-section tends to squeeze, and at the end we will have the break. The peak of this red curve is the sigma u, or sigma UTS is the ultimate tensile strength of our material, and sigma f is the sigma of the failure of our material, and sigma y is actually the sigma of the yielding of our material. Now let's describe the Hooke's law. A material behaves linearly in the elastic regime, as we saw before, and the linear relationship between stress and strain was discovered for the first time by Robert Hooke. And it is sigma equal to E times epsilon, where E is the modulus of elasticity, or Young modulus, and it is defined as the ratio between the sigma of proportional load and epsilon of the proportional load. We can also define the Poisson ratio. The Poisson ratio, Ni, is the quotient between the lateral and the longitudinal strain. So it is if we have that epsilon longitudinal is equal to delta over L and epsilon lateral is equal to delta prime over R, ni will be equal to minus epsilon lateral over epsilon longitudinal. And ni will be positive in this case with this minus. We can also define the rigidity modulus, G, or shear modulus of elasticity, and it is equal to E over 2, 1 plus ni. And the stress strain diagram can be produced also for shear stressing and measuring the angular strain and obtaining tau equal to gamma times G. Now let's enter more into detail in the shear and moment diagram bendy stresses in beams. Let's begin with shear and moment diagrams. So for convention, internal shear forces and distributed load are positive if acting upward. Moreover, internal shear forces caused a clockwise rotation, so you see that V caused a clockwise rotation, and internal bending moment is positive if it compresses the top fibers. So you see that these tend to compress this top fiber. Let's see the graphic representation. So if you have an isolated slice of a beam with a distributed load Wx, whose resultant is acting on the distance equal to k dx, that depends on the distribution. For example, for a uniform distribution, with a constant distribution, k will be equal to 1/2. We have that this infinitesimal slice has this moment, this internal moment acting, so m and m plus dm, v and v plus dv, and this distributed load. So if we write down the Newton-Euler equation of equilibrium, we find out that v plus w of x dx minus v plus dv must be equal to 0. So we yield that dv must be equal to wx dx. From the Euler equation, we have that v of x dx minus m minus w of x dx times k dx plus m plus dm must be equal to 0. So we have that dm is equal to w of x k dx squared plus v dx. So if we divide both equations by ax, and we know that dx squared can be neglected because it's an infinitesimal of the second order, we get that dv over dx is equal to w of x and dm over dx is equal to v. Let's now see the bending stresses in beams. So a beam subjected to a bending moment will be deformed, and the upper part will be subjected to a compression, while the lower part will be subjected to tension. The beam is continuous, therefore there will be a neutral surface in which the strain will be 0. For an infinitesimal slice, as we see in this figure, we can approximate the surface as arcs and define a radius rho, recalling the definition of the strain. So epsilon is equal to the limit of delta s going to 0 of delta s prime minus delta s over delta s, where delta s prime is equal to rho minus y times delta theta, and delta s is equal to rho times delta theta. So at the end, epsilon will be equal to the limit of delta theta going to 0 of rho minus y times delta theta minus rho delta theta over rho delta theta. At the end, we will get that epsilon is equal to minus y over rho. So the strain, in this case, is a linear function of the distance from the neutral surface, and it will be maximum at the maximum distance c. So epsilon maximum is equal to c over rho. So the radius rho can be expressed as a function of epsilon max using this formulation here, and we can rewrite epsilon as minus y over rho, which is equal to minus y over c times epsilon max. So we can now derive the formula of the flexure. We can assume that the material is elastic and linear, so we can apply the Hooke's law, and we can say that sigma is equal to epsilon times E. At the end, we will get that sigma is equal to minus y over c times sigma max. The actual location of the neutral axis is still unknown, so we can compute the position imposing the equilibrium of the Newton equation. So the resultant forces is equal to the sum of all the forces must be equal to 0. So 0 is equal to the integral over the area of the f which is equal to the integral over the area of sigma dA, which is equal to the integral over the area of minus y over c times sigma max dA. Since sigma max and c are independent from the area, we can bring it outside and find out that minus sigma max over c times the integral over the area of y dA must be equal to 0. And since sigma max is different than 0 and c is different than 0, we have that the integral over the area of y dA is equal to 0. And this is true if the neutral axis is in the centroid of the cross-section. We can also write down the Euler equation and write down that the resultant moment mr is equal to the sum of all the moments, and it is equal to m, the applied moment. So m is equal to the integral over the area of dm, and dm is actually y df, and df is equal to sigma dA. So at the end we get that m is equal to the integral over the area of y sigma dA, which is equal to the integral over the area of y times y over c times sigma max dA. And since sigma max and c are constant, they can be brought outside the integral, having that the moment is equal to sigma max over c times the integral over the area of y squared dA. And in this case, the integral over the area of y squared dA is actually the moment of inertia I. So at the end we get that sigma max is equal to the moment times c over the moment of inertia. And if we substitute this result in the definition of sigma, we have that sigma is equal to minus y over c times sigma max. Sigma max is this quantity here. So at the end, sigma will be equal to minus y over c times mc over I, and it is equal to minus my over I. So, and this is called the Flexure formula. We can now enter into torsion and torsional stresses in beams, and in particular in the torsional deformation. So the torsional deformation of a cylindrical shaft due to torsion can be described considering a body made of rubber. So circles and radial elements are not modified, while the longitudinal fibers are bended on a plane, as in figure below. The definition of shear strain is gamma equal to pi half minus theta prime, and we can isolate an infinitesimal slice of length dx and express theta prime and gamma. So this is our infinitesimal slice of length dx, and we can see that we can express the arc BD in two ways. For example, rho times d phi and dx times gamma. We can now express gamma as a function of rho and d phi over dx. But d phi over dx is constant along the cross-section, and the angular straight gamma grows linearly with the radius rho. So we have that d phi over dx is equal to gamma over rho, and it is equal to gamma max over c, where c is the maximum value of rho, and in this case is actually the radius of the shaft. So at the end we will have that gamma is equal to rho over c times gamma max. We can now see the torsion formula. So if we recall the Hooke's law and rigidity modulus g, we have that tau is equal to g gamma. And so tau max will be equal to g gamma max. And we can say that tau is equal to rho over c times tau max. So the infinitesimal force dF will be equal to tau dA, and the infinitesimal torque dt will be equal to rho dF. So the torque at the end will be equal to the integral over the area of rho times tau dA, which is equal to the integral over the area of rho times rho over c times tau max dA. Since tau max and c are constant, we have that the torque is equal to tau max over c times the integral over the area of rho squared dA. Actually, the integral over the area of rho squared dA is the polar moment of inertia j. So we can write out that tau max is equal to Tc over j, and exploiting this relationship, we can write down that tau is equal to T rho over j. We can now yield the definition of the twist angle. So the twist angle d phi is equal to gamma dx over rho, and since we have that from Hooke's law, gamma is equal to tau over g, so tau will be equal to T of x rho over j of x. t of x and j of x are function of the x coordinate, so it's function of the longitudinal coordinate. So in general, the phi will be equal to t of x over j of x times g times dx. For a shaft with constant cross-section, so j of x is equal to j, and a constant torque tx equal to t, the phi will be equal to t over gj times dx. And the integral of this expression is really trivial, and we get that the twist angle is equal to phi equal to TL over gj, where L is the length of the shaft.